Yeah, thank you very much, Joseph, for organizing this amazing conference and also all the other organizers. Ultracold atoms in optical lattices really form this amazing platform to use atomic physics to create very, very coherent many-body quantum systems. And so these many-body quantum systems, they are particles can strongly interact. You have natively, you can use bosons and fermionic degrees of freedom. You can implement them natively. It is very controllable. It is very controllable even on a single particle level, and that makes it really special. So ultracold atoms in lattices, they're not only the original platform for quantum simulation, but they're going really strong, as you saw in a number of talks here already. And in particular, they're getting more and more into regimes that are really difficult or near impossible to compute, and so that means that these quantum simulations get more and more useful. In my talk, I first want to tell you about some experiments that are really at this brink now, where it becomes pretty much impossible to compute things, even though the model is simple, but we can do quantum simulations. And then I will show you a bit how we extend that Hubbard toolbox more and more. I will tell you about artificial gauge fields, like strongly interacting gas, and some two-particle fractional quantum Hall physics, and towards dipolar quantum gases in optical lattices. So let's start with fermionic lithium atoms in an optical lattice. This is the wonderful team. And so it turns out if you have fermionic atoms in optical lattice, you have a practically perfect realization of the very famous Hubbard model that you see here, which seems very simple, right? Because all it describes is the tunneling of particles between neighboring sites. And if you have two particles on the same site, they repel each other, for example, leading to on-site interaction energy U here. And the particles are fermions, so they obey fermionic statistics. And so you can't have two of the same spin state on the same site, but we have two spin states, and so and then they move on the lattice. Really simple, but this is really this is deceivingly simple, because it turns out this Hamiltonian, it's not even quite clear how the phase diagram exactly looks like, or what the low temperature phases, what the physics is here. It is believed that it looks a lot like the phase diagram that has been measured for high temperature superconductors, and so there's this very strong connection, and learning more about the Hubbard model could also really help understanding things like D-wave superconductivity better. At high temperatures, you have a metal. As you lower the temperature below the interaction energy, you get a Mott insulator, one particle per site. The spin is still random. But surprisingly, if you go even lower, then the spins start to order. Why is that? There is no explicit spin-spin interaction here, right? But you have super exchange. There is like a second-order process which favors opposite spins. You can easily understand this. The same spins can't even go to the neighboring site virtually, but if they're opposite, they can go virtually and exchange or go back. And so that's why at low enough temperatures and at half filling, you get a Heisenberg antiferromagnet. In the experiment, so here's a picture of a Mott insulator, but if you measure the spins and also get the temperature very cold so that super exchange becomes dominant, then you see these kind of like checkerboard-like patterns that show you the magnet. At cold enough temperature, it's really long range, as big as the system, kind of antiferromagnetism. But keep in mind, this is a bit simplified here. In reality, you really have a Heisenberg quantum magnet, which is quite a bit more rich than just a simple Néel-ordered state. So this is at half filling here on this line. But things get really rich and complicated once you add some additional charge carriers. For example, holes. So if we hole dope the system, then at low enough temperatures, all of these phases are expected, like strange metal phases, a pseudo-gap phase, and so on. And there was quite some activity in quantum simulation. I don't have time to discuss this all in detail, but have a look at this recent review that reviews the experiments in this doped regime. It all started with experiments in Zurich, but then with a microscope, this got a big boost, and so now we're getting to colder and colder temperatures here. Good. So why do things become so much more complex and interesting once you dope the magnet? Well, first of all, in 1D, it's actually very simple. There you have perfect spin-charge separation nearly. And that was recently nicely shown by the group in Munich. But in 2D, things are really complex. And with this cartoon-like picture where I just show like a naive Neal ordering, let me show you a little bit the spirit of the kind of things that are happening here. If you have a hole in this magnet, and now this hole wants to move or delocalize, if it moves horizontally and then vertically here, you see that it leaves behind a trace of atoms in the wrong spin state. These have unhappy bonds, so this costs energy, may not even be possible. Maybe this only happens virtually, but this is in principle an old idea, but more recently there were interesting ideas to take this a bit more serious and really talk about a gas of these mesons that are made up of the magnetism and the additional charge carriers. And so you can kind of think of this whole bound via a spring to a spinon. This may or may not be a good description. Like numerically, it wasn't quite clear, but we have started to do a series of experiments to really test these kind of ideas and theories and see how we should think about these doped phases. But in any case, you will have some kind of polaronic motion, and so that's what I will mostly talk about today. In equilibrium, we have seen evidence for these string excitations, these rows of spins in the wrong spin state, and compared that to theory, and there's also some nice recent work in equilibrium on the polarons. But let me focus on one part today where we really directly study the dynamics of a hole in this antiferromagnet. The idea is we create a single hole by just blocking one lattice site with a laser beam and creating a half-filling antiferromagnet around it. And we can do this in a fairly large system, so this would be very hard to compute the dynamics in a system like this of about 20 by 20 sites. And then we pull the plug. Then we turn off the potential that's created with the spatial light modulator. And so the hole can move now, and we see where it moves to. Of course, we take a lot of pictures for statistics, since there are also some other hole with like hole double-on excitations and so on. But we can do that. And so what you kind of expect is polarons forming, polarons spreading. Let's see if we find evidence for that. Let's first look at the density directly. So here the density is plotted, which is averaged over the symmetry axis here. And you see, as time passes, you see how the hole spreads out. And if you compare this to a simple quantum walk, you see that at first it behaves just like a quantum walk for the first tunneling step, but then it deviates strongly. And of course, that's what you would expect. Let's plot the distance the hole has traveled as a function of time. And again, it's a fairly large system. And so what we see is that initially the hole moves away just ballistically, just as you would expect from a quantum walk. So this is on the tunneling time scale. But then things start to slow down, and we see that at later times, the hole moves significantly more slowly. Is this because it has formed a polaron and now has this kind of hybrid object of magnetic excitation around the hole? Well, if this is the case, then the magnetism would now set the time scale for this motion. So how can we test that, if it's magnetism or just the tunneling? Let's change the magnetic interaction strength, J. We can do it with a Feshbach resonance by changing U if we make the magnetic interaction half as big, we find that indeed the motion of the hole over long distances, here 4, 5, 6 lattice sites, is only about half as fast, right? And so that's nice evidence that, yeah, this hole is forming a polaron, and it's now the magnetism that determines the motion of the hole. Yeah. We've done some more experiments also investigating the magnetic environment around the hole, but I refer you to the paper for those details. Good, so that's interesting. So if you have polarons, right, and we can study them, and we see the magnetism plays an important role, can we maybe what happens if you have multiple polarons? So that's what we want to try in the future. Imagine you have 2 polarons, and you see, do they move independently or in a correlated fashion, right? And if they move correlatedly, well, is this maybe a D-wave Cooper pair, some interaction between these polarons? Is that how we should think about it? Nobody knows, but you're looking very much forward to doing experiments like that. One important point is here, so compared to quantum simulation on like quantum computing platforms like spin models or so, it's really huge that we can natively implement the fermionic degree of freedom here. If you map that onto qubits, you pay a huge overhead, and a local model becomes a highly non-local model and so on. So this is why these Fermi-Hubbard quantum simulation for problems like condensed matter problems, but maybe also chemistry and so on in the future, are really, really powerful. Good, so I showed you the Fermi-Hubbard. By the way, in the last year and a half or so, we are going through a major upgrade of our optical lattice. We expect to get much colder temperatures soon. We have lower heating rates. We have implemented all kind of ways to try to lower the temperature, and we will be able to also make triangular and hexagonal lattices, so stay tuned. Well, in the next part of the talk, I want to show you a different way how we can really extend the Hubbard toolbox, and the idea is to do strongly interacting topological physics here. And so this is done in the rubidium lab. So these are bosonic atoms on the lattice. Here's the team. So Shin is here. And so how can we simulate the motion of charged particles in a magnetic field? What we need to engineer complex value tunneling in the lattice, right? If you have that in some kind of spatially dependent way, then you can create a situation that if a particle tunnels on a closed path, it will actually pick up a phase that is proportional to the area, so that is the same as a charged particle in a magnetic field. How do we do that? Well, first, we take a lattice. First of all, we tilt it to turn off any tunneling. But then by shaking it, we can reestablish tunneling via a 2-photon process. And if we shake it kind of out of sync in different lattice sites, then this can be spatially dependent and corresponds to a complex tunneling phase. So that's exactly what we need. There have been interesting experiments along these lines in many labs, mostly for non-interacting or very weakly interacting situations. But if you have strongly interacting particles in such a potential, then you expect to get Laughlin states and fractional quantum Hall physics. And so that's what we are after. Again, there were some nice experiments along those lines, but let me just point out, if you talk about Laughlin states, there are 2 nice examples. So one is by the group of Steve Chu and Nate and Edina, where they saw 2-particle Laughlin state in like single traps, essentially, where they saw evidence for that, and recently, amazingly, with photons. So in the next talk by John, with photons, where you get Laughlin states of light, the photons interact strongly via Rydberg interaction. Anyway, let's do it in the lattice. So what do we, let's use 2 particles to start also. And the smallest lattice where we could do this in a meaningful way is like 4 by 4 lattice sites. we initialize, so at first we tilt that lattice and initialize the ground state, which is just a Mott insulator of 2 atoms down in the tilted corner here. And then we can release the tilt, spread those particles out into a 1D superfluid, and then the other direction to make a 2D superfluid. And we can go back and forth, and by checking how well we get back our initial state, because this is a Mott insulator, there's no entanglement, by looking how well we get this back, we can directly measure the fidelity of this adiabatic many-body transfer, or well, two-body transfer for now. Here I have plotted the gap of this system of 2 particles on 4x4 as a function of this tilt I was describing, the tilt to delocalize the 1D system into 2D, and as a function of the flux. Let's first focus on no flux here. So if we release the tilt here, we create this situation, but then we can go back and forth and see how well we turn back. And we see that we can turn all the way back and forth to a 4x4 system with about 70% return probability, so that from that we estimate we have about 85% fidelity in the preparation of delocalizing these 2 particles completely coherently on the 4x4 system. Okay, I apologize for the color scale. They have to change that, but so this plot shows the gap, and actually let me go back here real quick. You can kind of see here is an island of finite size gap. This is where we expect the fractional quantum Hall state. So can we just do the same now going down straight here? Well, one thing you may notice is that in the middle here, this is very dark blue, so here the gap kind of vanishes. And so indeed, if we try that, we get an extremely poor return fidelity. We cannot just go down the same way. We need to find a path for the adiabatic preparation that has no gap closing. Can we do that? Well, we need to vary some more parameters. Let's vary the ratio of the tunneling in X and Y. And if you do that, you see that now there is a bridge here of a good-sized gap, essentially. So could we go here? This would be nice, but unfortunately, if you tune our flux dynamically, that leads to some heating, so that also did not work particularly well. Are there other kind of bridges? If you tune it this way, now it gets even worse. Here, the gap closing gets even more severe. But if you move it the other way, if you keep a finite ratio in X and Y tunneling, then you actually see that there's a continuous connection here. And so the idea would be to go down here and then cross over here, make the tunneling equal in X and Y, and go to the fractional quantum Hall state. So we have first tried to release the ramp this way here, and we get pretty decent return fidelity everywhere here. But if you now try to go down and over to equal tunneling in X and Y, then we see that we can indeed do this with decent return fidelity in the normal state. We can also do it with decent fidelity in the place where we expect the fractional quantum Hall state. But in between, where we expect the gap closing, in fact, we see that the return probability vanishes. And so this strongly suggests that we really are able here to prepare the fractional quantum Hall state of 2 particles. How can you probe it? Like, what are the properties? Well, the easiest way for us atomic physicists to understand such fractional quantum Hall state is the 2 particles just sit in each other's vortices, right? They're both in a gauge field where where the wave function has zeros, where they disappear. They want to repel each other, hence avoid each other, and they can do that by moving into each other's zero of the wave function, right? And so that is the Laughlin-like state, but that means you should have a reduced probability to find 2 particles on the same site, and our data is very consistent with that. So what is really nice is that if you do calculations with 3 and 4 particles, you still have very similar size gaps. Again, sorry for the color scale, but the gaps here are nearly the same size, so that seems quite feasible to do. And what's nice is that theorists tell us that if you look at the entanglement spectrum, for example, these kind of states already have all the features that the fractional quantum Hall physics is known for. So we are very much looking forward to some experiments along those lines. Good. So in the last few minutes, let me tell you about the progress of experiments with dipolar quantum gases in optical lattices. This is our new Erbium experiment. I mean, new by now. There was also one generation of students already, because these experiments, of course, get more and more complex. And we started this experiment in collaboration with Francesca Ferlino in Innsbruck. Yeah, so the nice thing is that these erbium atoms are quite magnetic, right? They have 7 mu Bohr magneton, and so that means that we can study high polar physics with them, like you also saw in some previous talks already, which is interesting because these are long range or longer range forces and anisotropic forces. But erbium also has some other nice properties. There are, for example, very narrow lines that we can use for narrow line laser cooling. And so what we do is we use an 8 kilohertz white line to cool the quantum gas very close to degeneracy via laser cooling. And then the remaining evaporation we can do in just a few hundred milliseconds here. And so in a total of about 700-800 milliseconds, we can then get a good size BEC. That is nice because the cycle time for a lot of our quantum simulation experiment is really the limiting factor. The experiments typically run day and night, and so if you're like 30 times faster than traditional experiments, that's huge. It's kind of the same kind of speed that you would get in a tweezer experiment, but of course here we have hundreds of thousands of atoms in the BEC after that time. In order to maximize the dipolar interaction strength, well, it's a fairly weak interaction still, we need to space the atoms as closely as possible. And we do this by using a green lattice where we have a lattice spacing of 266 nanometers. Right? With that, we get about 30 hertz dipole-dipole interaction between neighboring atoms. And so that's kind of getting close. It's just a few times smaller than our than the on-site interaction, for example, in the rubidium experiment. But with this very small lattice spacing, how can we now do quantum gas microscopy? How can we image individual atoms in such a small spacing lattice? Well, the first thing we need is a the first thing we need is to is a high-resolution objective, and so we use we need a very good objective, and so we use an in-vacuum objective with a numerical aperture that is as high as it can be here. But then we do an additional trick. So instead of just trying to image the atoms in that tight spacing lattice, we actually use an accordion lattice to zoom in, like to increase the spacing of the atoms before imaging. And so we blend over from this green standing wave lattice into a lattice that is formed by blue laser beams and the objective. And if you then move the laser beams in the Fourier plane of the objective, we can increase the lattice spacing up to about 5 micron. Here's a little video. This is the vacuum chamber where the objective is inside. And up here in the Fourier plane, you can see the laser beams that are steered via galvos, essentially. And so that works actually quite nicely. Once we increase the spacing, then the idea was to do simple flash photography. Like normally you do laser cooling in a lattice, and it's quite complicated, and even more complicated here, because if you use a narrow transition, you only scatter photons slowly, and so on and so on. So the idea was to just do flash photography, just flash it on the light for a very brief moment and collect as many photons as you can before the atom moves away. So how does that work? If you just illuminate it from one side here, then actually you would push the atoms away very quickly. So we have like a 30 megahertz wide transition that we saturate. So you want to balance that, and we tried for a while to have two beams, and even if they don't interfere, we still get really strong mechanical forces. I think there's actually some interesting atomic physics, so if you have some thoughts on that. But we didn't want to study atomic physics here, we wanted to image the atoms, and so in talking to Selim Jochen's group, we actually learned that there's a neat trick. If you just blink it very quickly, like a few nanoseconds between the beams, then you can very nicely scatter a lot of photons. And in our case, we scatter we detect 40 photons within 5 microseconds of scattering time. And you can see from the picture that we get a very nice fidelity here. So 40 photons is, if the point-sparse functions don't overlap because of the accordion lattice, then these 40 photons are plenty signal to measure the individual atoms with high fidelity. Yeah, so this is coming along, and we can't wait to try to do some high polar physics in the optical lattice and work with that quantum gas microscope. Good, so I showed you a quantum simulation with Fermi-Hubbard, right? Fermions make it really powerful, but then we can also extend the Hubbard toolbox to strongly interacting system and gauge fields and dipolar physics. And I would like to thank the whole team who has worked, who put a lot of effort into these experiments. I always make it sound simple in a talk like this, but you know how much goes into it on all the different levels. These experiments are technically very complicated, and so I have a really high respect of everyone working in the team there. And I would also like to thank the sponsors, and thank you very much for your attention.
Great, thank you for that beautiful talk. We have plenty of time for questions. Let's start here, and then here.
Hey, Markus, nice talk. How will you do thermometry below the nail temperature?
So we are still in a regime where we could win by, like if you look at a long-range correlation, we can certainly still look how that exactly scales. We're also playing with coupled systems, coupled layers ultimately, so that would be useful. But no, it's a very interesting question, and I think that will go hand in hand, how to try to lower temperatures and how to try to then detect that temperature. Another way is if you do this adiabatic transferring back and forth, right? Like let's say one of the things we want to do, we know we can create extremely cold band insulators, and then we want to adiabatically transfer into an interesting many-body state. And kind of similar to what I showed in the bosonic experiment, if you then go back, we can see how much entropy we have created. And so that's also a nice way to measure really, really low entropies.
Thank you.
Markus, fantastic. Congratulations. One of the most fascinating things in the fractional quantum Hall physics are obviously excitations, because for the standard Laughlin state, these are anyons. For Pfaffian state, which you also are on your agenda, have on your agenda, they are even non-abelian anyons and things like that. Is there any chance for somehow studying excitations in such small systems, and then if, how?
I think so. So again, you would probably want like a 3-4 particle, like with a 4-particle system or so. You could imagine to do that. We have looked into some proposals where you have where you can try to resonantly drive them, or where you can split the system into 2 systems and connect it again and see how the entropy changes. But actually, I would love to discuss that actually, and I'm sure you guys may have good ideas, because we can do, the system is very programmable, so whatever you tell us to do, in kind of we could in principle do it. One other way is if we move, for example, we're developing methods to smoothly move like an obstruction around, for example. So that could be a nice way for this. And in fact, we are preparing this for the Rydberg experiments that I'm also involved in with Misha Luke and so on. So there, we recently developed a system where we should be able to move these topological excitations. So there are many ideas, yeah.
So in the experiments where you were looking for fractional quantum Hall effect, one of the things you were trying to do these adiabatic paths, and one of the things you were looking at to judge the quality of adiabaticity was the return probability. Now, if I read the things correctly, you were saying that good return probabilities were in the 30 to 40%, which objectively doesn't sound that good. So why is it okay to have a return probability that's only that good?
Yeah. It depends on the observable, right? How, if that's good enough or not, or it kind of translates into something like over an ensemble average, something like an effective temperature or so, right? And some properties would disappear once you have one excitation in the system, but other properties may also be a bit more robust. So for example, at least for the 4-particle systems, we did some simulation assuming to look at the lowest excitations, and some of them actually still have the relevant properties, right? So this depends a lot. I mean, ideally also, this is also a little bit at the edge of what the system has not been designed really to do these kind of experiments. This is kind of pushing it. I think if you were to design a system, and there are a lot of systems coming up that start with a tweezer array or so, if you start to design it, you could do things much more. You should be able to get those fidelities really up a lot, because some of these fidelities are daily fluctuations. Like on one day we get really good fidelity, and then on the next day it's not so good, and then we average data sets. And so I think there is a lot of room, and we're quite happy for now, but there's certainly room for improvement. But then it depends. I think it's an interesting, more general question: how cold do you have to be to still get the relevant physics? And I mean, as you know, in all of the BEC experiment, I'm talking about the actual probability to be in the ground state, right? Yeah. In a lot of BEC experiments, there are some excitations, but it doesn't matter. The many-body physics still doesn't care too much about it. So I think it's interesting open questions that theorists also couldn't tell us clearly yet, but we start to investigate that. How many excitations can we afford?
So so one of the things you're saying is that this return probability may be a little bit deceiving in that it doesn't necessarily really represent that much excitation.
Exactly. It's actually measuring the many-body purity,
yeah,
right?
Right.
Yeah.
Yeah.
All right. Any further questions? Yes.
More technical question, Markus. If you transfer from the 266 nanometer lattice with the Erbium experiment into a projected lattice, how do you register the 2 lattices with respect to each other? Don't you need, a few nanometer relative alignment of the 2 lattices to?
So this part actually worked much better than I had hoped. So first of all, the standing wave green lattice is created by a mirror mounted to the vacuum chamber. So that's quite stable. And then the other lattice is defined by the objective position, essentially. And we actually find that the two only fluctuate by much less than a lattice height per hour. I mean, we do have a good temperature stability in our lab, that's important, but it's actually quite good. But then even better, it's very easy in a single shot to measure the relative positioning. You do just a moire, like make one lattice slightly larger than the other, one lattice spacing, and then you see the stripes where they don't match. And with a single shot, you know how far you're off, and you can immediately go back. And this is a repetition rate of 1 second or so, right? So, you know, if you, like even if you have to retweak it once a minute, once every 60 shots or so, that's no big deal.
Great. Let's thank Markus again.